Chapter 1, Chemical Foundations. Your book actually has a preceding chapter that goes through some essential materials like dimensional analysis, units, exponents, scientific notation. We will cover some of that a little bit in here, but I will make a separate video and point you to that for review if you need some review on that. It's a highly important and strongly recommended video to watch, but because it's not part of this chapter, it's not going to show up here. So let's look into chapter 1. So chemistry, we're going to start out here as our table of contents. We're going to talk about the atom's first approach, talk about the scientific method, some of the early history of chemistry, our fundamental chemical laws, Dalton's atomic theory, early experiments to categorize the atom, and then the modern view of atomic structure, so an introduction to that. So we're going to ask, what are atoms made out of? How are they arranged in molecules and ions that make up the substances that we encounter every day? And how do we associate the name of a substance with its chemical formula? So that's some of the big questions that we're going to start to address. So what is chemistry? Chemistry is the study of matter and the changes that matter undergoes. This would also be a good definition question on an exam or a quiz. Matter is anything that has mass and occupies space. So anytime somebody says a product is chemical free, if you can hold it in your hand, it has chemicals in it. The nature of those chemicals may be different, but anything that has matter is a chemical. So we're looking at the study of matter and the physical world. To visualize chemistry and these atoms, because they are very, very, very small things, this text, the macroscopic and the molecular level, will be explored using molecular models, and we're going to represent each by a particular color. This is kind of standardized throughout most textbooks and how people represent these. So hydrogen is going to be a little white ball, carbon will be a black ball, nitrogen is blue, oxygen is red, fluorine is kind of yellowish greenish, sulfur is yellow, sodium is gray like the metal, chlorine is green, bromine is kind of orangish brown, and iodine is purple. We have different levels of representation for our molecular models. They go from a text formula, so H2O, which uses our atomic symbols, to a ball and stick model, which shows the connectivity of the atoms in a molecule, and then a space-filling model, which shows the actual volume in 3 dimensions that molecule takes up. And they're all useful in different contexts. Right? So the text formula obviously is going to be the easiest to use, but it's going to have the least amount of information. The space filling is going to have the most information, but it's also going to be the hardest for you to use on a daily basis. I would not want to try to do a balanced chemical equation, for example, using space filling models. Right? So the importance about studying atoms is that it provides a better understanding about the macroscopic structure and the behavior of matter. We're going to look at the formation of different molecules and the attraction between different molecules or repulsion. The study of chemistry is based on a proper understanding of atoms, and this forms the basis of solutions to many, many problems. Some of the stuff, particularly in the next course in the sequence, is going to look a lot at energy, but we're looking primarily at atoms in this course. And electrons. So knowing about electrons is really the key to understanding 120. So here is a picture of some atoms as seen through an STM. It's a scanning tunneling microscope. So you are actually able to visualize, and we can use this specialized microscope. So each of these little bumps in here represents an atom. You may have seen the picture where somebody has spelled out the word IBM and xenon atoms, but each of these things represents an individual atom. So we can actually image things down to the atomic level now, either with an atomic force or another scanning probe type of microscopy, which is a technique that I use quite extensively in graduate school. So understanding atoms, the macroscopic world comprises objects such as cars, rocks, oceans, etc. And all of these things are made up of individual atoms. Now for us, we're not going to spend too much time delving into what happens if you start breaking apart atoms. So we're going to treat atoms as being discrete and elements as being discrete. But we will see that the atoms are actually made up of smaller subatomic particles. The understanding of the structure and behavior of different atoms, each element is a different type of atom, and each element behaves differently. Some groups of elements are going to behave similarly to each other. So, all metals kind of are metallic, and we've got non-metals that are non-metallic, and they've got different characteristics to them. And it's going to help give us a better purview of the macroscopic world. So we have the macroscopic world, which is our visual world, the world that we live in and move about in. And then we have this very, very, very small world, the microscopic world, that exists on the level of individual atoms. So the macroscopic world comprises our big objects, right? They are made up of the atoms. And understanding the structure and behavior of these different atoms gives us that understanding of the macroscopic world. And it's all about, for us, understanding how those electrons work. And so the electron structure is going to be really, really important in our fundamental study of atomic behavior. So let's look at grains of sand on a beach. Each of those individual grains of sand is made up of atoms. In this case, it's atoms of silicon and oxygen, it's SiO2, in a network solid. So even though we've got billions and billions of grains of sand on the beach, then we've got even smaller components. Those are individual atoms. And this is where, the sand people were walking single file to hide their numbers. So the stuff things are made out of. We've got matter. So all stuff is made out of matter. And all of our matter, at least on our Chem 120 level, is going to be made up of atoms. And those atoms come in different varieties called elements. Right? And we have a very modern view of that based on the periodic table, where we've grouped these things in a very systematic way, and it's actually based on their electronic structure. And this differs from the classical, historical, Aristotelian, and Empedoclean view, which has the 4 different elements: earth, air, fire, and water. Now, if you were Chinese, you'd have a 5th one, and you'd have wood and metal instead. So, there are other ways to describe it. We're using a definition of an element that is based on atoms. So matter is either classified as a substance or a mixture of substance. A substance can either be an element, a pure element, or a compound, which is going to have a definite or constant composition and distinct properties. So sodium chloride is an example of a substance that is a compound. It is made up of sodium and chlorine. Water is a compound. Oxygen is an element. So the oxygen in our air is an element. It's made up of 2 oxygen atoms stuck together. An element cannot be separated into simpler substances by chemical means, and it is defined, as we will find out, by the number of protons in that atom. Examples: iron, mercury, oxygen, hydrogen are all elements that you should be familiar with. Compounds are 2 or more elements chemically combined in definite ratios. So H2O, 2 hydrogens, 1 oxygen. SiO2, 1 silicon, 2 oxygen. And these cannot be separated by physical means. We can rearrange the elements in a compound to make new compounds, right? And that's the basis of a chemical reaction. So, for example, if I take sodium metal and chlorine gas, and I combine them together, they're going to go boom, and they're going to make sodium chloride salt. If I take hydrogen gas and oxygen gas, I can make water, right? I can rearrange those elements and the arrangements of those elements chemically to form new compounds. Carbon dioxide, right? So if you inhale oxygen and exhale carbon dioxide, you've rearranged, you've made some new compounds, but those compounds are going to exist in definite ratios for that compound type, right? And they're going to be composed of 2 or more different types of atoms. A mixture is a combination of 2 or more substances. The substances could be elements, or they could be compounds. The substances are going to retain their distinct identities. Right? They're not going to have a universal constant composition. So if you think about something like sweet tea, right? Sweet tea is a nice mixture, but if you buy sweet tea down in Georgia, and if you buy sweet tea up in Vermont, right, they're going to be 2 radically different compositions. So it's not universally constant. They can be separated by physical means. So if you've got sugar and iron, right, you could separate those magnetically. If you've got sugar and water, you can evaporate off the water. So mixtures are separatable by physical means. They are composed of two or more substances, and their particular composition can be varied. We've got two different types of mixtures. They can either be homogeneous or homogeneous, or they can be heterogeneous or heterogeneous. Either pronunciation is valid. In a homogeneous mixture, the composition of the mixture is uniform throughout. So think of that sweet tea. Okay? Heterogeneous means that the composition is not uniform. Think of something like a chocolate chip cookie, right? You're not evenly distributing that chocolate throughout the cookie. So here is a little flow chart that you can use to describe your matter. So you got some matter. It can be either a mixture or it can be a pure substance. You can take your mixture and separate it by a physical means into pure substances. Your mixtures, we said, had two types, homogeneous or heterogeneous. Our pure substances, we can break down into either compounds or elements. And if we take our compounds, we can separate those by chemical means into their distinct elements. So let's take a quick second and classify some of the following. All right, so aluminum foil is an element. Baking soda is a compound. Curdled milk is a heterogeneous mixture. Air is a homogeneous mixture, and copper wire is an element. For purposes of our class, our matter can exist in three states. It can either be a solid, a liquid, or a gas. So this is a visual representation of solid, liquid, and gas. There are other states of matter out there, right? So the sun, for example, is not a massive incandescent gas. It is a miasma of incandescent plasma. So that plasma is an excited state with no electrons on it. You can have something like a Bose-Einstein condensate at very, very low temperatures. So you get these weird exotic states of matter in the realms that we are working with, kind of around normal human operating range. We're going to have solid, liquid, and gas. A solid, the particles are close together and in an orderly fashion. There's little freedom of motion, and it does not conform to the shape of its container. So its shape is static. In a liquid, the particles are close together, but they're not held rigidly in position. They're free to move past one another. And a liquid is going to conform to the shape of the part of the container that it fills. And finally, we've got a gas. So this is particles moving randomly. They're spread far apart. They have complete freedom of movement, and they're going to assume both the shape and the volume of the container. States of matter can be interconverted without changing their chemical composition. So if you take a solid, you add some heat, you can liquefy it. You add a little bit more heat, it can go to a gas. Right? You can go the other way, cool a gas to a liquid, a solid. There are other transitions, and we will talk about those in Chem 130. For example, sublimation, where you're going directly from a solid to a gas, like in dry ice, or deposition, where you're going from a gas to a solid. So there are only about 118 specifically. So I tried to put my notes in purple here. And there are only about 100 different types of atoms. They're going to combine in various proportions to form all known substances. Everything is a chemical, even organic stuff. So there is no chemical-free whatever. Organic stuff, if you are a scientist, just means that it has carbon in it. So any pesticide that you get is going to be organic. But then again, so is VX gas. VX gas is organic. Properties of a substance are determined by the arrangement of its atoms. So looking at the difference between atoms and molecules, we said that matter is composed of tiny particles called atoms. The atom is the smallest part of an element that is still an element, and our molecule is two or more atoms joined together acting as a unit. So you got hydrogen and oxygen atoms here, and they will combine to form a water molecule. Chemical elements naturally. We have some chemical elements that are called diatomic. There's a lot of these, so that's why we're bringing it up early on. So oxygen molecule is going to be O2. Hydrogen molecule, H2. Others would be like Cl2, N2. A lot of these gases in their natural state are going to be diatomics. A chemical reaction is when one substance changes into another by reorganizing the way the atoms are attached to each other. And there are factors in here about energy and about electrons. And so if we've got two water molecules, we apply an electric current, we can back form an oxygen molecule and two hydrogen molecules. And so we can interconvert between molecules chemically. That's the basis